Okay, before I do a couple problems here, I want to just explain what's going on with these two chapters. First of all, we have different types of tests. We have, when we test a mean with one sample, we do either a z-test, or a t-test. And these look very the same, except you'll notice the t-distribution has more weight under the tails, right? And this is more robust, and it works better for smaller samples when sigma is unknown. And since sigma is rarely known, because if we knew sigma, we usually would know the population mean, and then why would we need to test the population mean? If we knew sigma and the population mean, we wouldn't need to test the population mean. So this is the one that is used in almost all studies. Okay. Then when we want to test a proportion or a percent, we use a binomial distribution, which is also this, which we can also approximate to a normal curve. So it's called a prop z-test. A proportion z-test, and that is really just approximating the binomial distribution, either something happened or it didn't, using a normal curve. You can actually use an exact binomial test as well, which uses the binomial distribution in binomial CDF and counts up, the probabilities of each. And then if we want to test sigma, we want to know whether a standard deviation from a sample is what we expect it to be in a population. Then we use a distribution called chi-squared. We're going to use this distribution for a couple different things, but one sample variance test uses sigma, and that's the one we're going to talk about today. Uses chi-squared. Chi-squared is what happens when you take a normal distribution and you square it, and then you add it together multiple times. So that's why it's called chi-squared. And you test sigma, you test standard deviations from one sample with this. We say, is the standard deviation what I expect it to be or not? The chi-squared test is also used to test count deviation, like how far off from a particular count is something than what I expected it to be. But that will come towards the end of this term. So you were asked to do some chi-squared tests in the lab, and that would have normally been a week. It would have been normally a week 9 lab in the full course, because there are 5 labs that we have to do, and so I didn't realize the spacing would be so far off with this lab, so I might have to fix that in the next term. But thanks for kind of going through it. So here we go. So I'm going to go through a one sample chi-square test for you right now. It says the 2013 General Social Survey asked how many times spent watching TV each day. The mean number was this, with a standard deviation 2.3. Assume a sample of 43 teenagers was sampled, and we're going to test if the standard deviation of the teenagers is the same as the standard deviation of the General Social Survey. So we're going to test to see if these are the same or not. If this group shares the same standard deviation or the same variance, right? So the first thing, this procedure is called a chi-squared test for variance. Right? So it is called a chi-squared test for variance. Right? The things that we know are true about this is that it's a simple random sample, so we need that. You need some sort of like random sampling. You need the population standard deviation is unknown. If it was known, then we wouldn't have to worry about that. And we need a normal distribution on this. Okay, so those are the things that we're kind of looking for on in terms of assumptions made. From here, hang on a second here. So this option is going to say one variance chi-squared. All right, and then it says we want to state the hypothesis, so we're stating sigma. We're testing sigma squared, so variance. And we want to see, is that 2.3, like we expect from the general population, or is sigma less than 2.3? And this should be squared because this is standard deviation, and we are testing variance. So make sure you take this 2.3 and square it so that it's in the same units, right? Where sigma squared, where sigma, it's the option, is the population standard deviation, and the units are in 2.3 hours. We're talking about hours. And this test is a chi-square test. And it is a left tail. All right, so that should be helpful. And the significance level we see in the problem is 5%. So that should answer your part 1 and part 2. Okay, so now we're going to compute the statistic that we need here. And the statistic for this, there are not shortcuts in calculators for this. And there really don't need to be because it's a really easy statistic. The chi-square test statistic is simply, is simply chi-squared equals n minus 1 times s squared divided by sigma squared. So if I go back to my problem here real quick and read through that, I know that my sample standard deviation according to the problem was 1.9. So if I square that, it's going to be 1.9 squared. And I know that my sample size was 43. So n minus 1 is 42. And then sigma squared is what was in the hypothesis statement. This comes from the hypothesis statement, is 2.3 squared. All right, so all I'm going to do to calculate this number is go 42 times 1.9 squared divided by 2.3 squared. And this is going to provide me a number. The closer this number is to 1, then the less likely I am going to reject. And or actually not to 1, the closer this number is to the sample size, the less likely I am to reject. So this is going to be my test statistic. And it's going to say, where it says select answer, it's going to be chi-squared equals, and then whatever this number is. Rounded to 3 places ends up being 28.662. Now I need to find a critical value. This is a left tail test. So, and I'm looking for 5% of the area on the left tail. Right, there's 2 ways that I can do this. One, using a calculator. I think you're using a TI-89. So you would go to test, distribution, go down to inverse, go inverse chi-squared. Then it will ask for an area and a degrees of freedom. For the area, you put 0.05 because it always gives you left tail. And then for the degrees of freedom, you put 42, right? So there's no, this DNA, this does not, you can put, does not exist, or does it apply? You could put DNA there, D and E, because you don't need to use that. It's not applicable, right? When you do this on your calculator, you should get a 28.144, right? So if you think about this, this is 28.144. Our test statistic is outside the critical region, right? To find the p-value, you're going to use on your calculator again, or you can also do this on Minitab. If I do, go to Minitab. I'm not sure I'll get enough decimal points, so I'll run through it real quick right now. Go to Minitab, go to Calculate, go to Probability Distributions, choose Inverse Cumulative Distribution, Single Value we're going to put 0.05 for left tail, 0.05. Normal, go to the chi-squared, which is the fourth one off the list after beta. Degrees of freedom is 42, n minus 1. Hit OK, and you do get plenty of decimal spots for that, 28.1440. Right, now I'm going to do the p-value. The p-value is looking from the test statistic, from this 28.662, and the area to the left of that, because it's a left-tailed test. So I'm going to go either in my calculator, I'm going to choose distribution. I'm going to go find the one that says normal or chi-squared CDF. The 89 has that, so easy breezy. Then I'm going to go in mini tab. I'm going to do the same thing. Cumulative density function. Calculate cumulative density function where it says value. I'm going to put 28.662. And I'm going to choose the chi-squared distribution. And my degrees of freedom is going to be 42. And this is going to come out at 0.0580588. Now, isn't that nice? See how close these two numbers are? So doesn't it make sense that the 5% would be just a touch over 5%? So we do not reject. It's not in the rejection alpha. P-value is not less than alpha. And so the conclusion is do not reject. At a 5% level, we do not have enough evidence to reject the null hypothesis in favor of the alternative. So hopefully that gives you a good sense of how to do that. I will take a quick look again at the next and just kind of real briefly run you through this process one more time. And again, this is a different test. We're not testing means, we're testing chi-squared distributions for variance. We're asking, is the variance of our new sample what we expected the variance of that population to be? All right, so it's the same kind of idea, the same steps of hypothesis testing, just instead of testing means or proportions, we are testing variances. So sorry about all the background noise. I'm actually on vacation. So here we go. We'll take this one real quick. All right, so this is the next one. All right, this one gave us a bunch of data. So the same thing, you're going to start with, chi-squared equal to whatever that number is in the problem. So for my problem number 10, or number 8, I'm sorry, sample bursts, 32 girls, so n is 32, given in this results, and then they gave me this standard deviation per sample. They want to know, is it the same as boys, which is 550. All right, so this is a chi-squared for variance. And then test is sigma squared. Again, we're testing against boys. This is what we're testing against. Please remember to square it because they gave you in standard deviation. And it says is less than, is girls less than, again, a left-tailed test. All right. This test is a left-tailed. The significance level is, they give us in the problem, 5%, so 0.05. Now, they're looking for critical values. You can use a table. I am not providing tables on the test. They give you a table here. I am not providing them for the test. So please know how to use technology to get these. Again, distribution on your calculator. Go to inverse, and then choose the chi-squared. And then the area. Here, it's a left tail, 0.05. If it was the right tail, you do 0.95. And then your degrees of freedom is 1 minus 32, which is 31. So you go from there. So, and then to calculate the p-value, you're going to find your test statistic. Your test statistic is this, 31 times 31.701 squared over 550 squared. And that test statistic is going to end up being 10.299. We're going to find the the value of that. Got a chi-squared. We're looking for the value to the left of this. Use inverse chi-squared, chi-squared PDF, CDF, chi-squared CDF on your calculator or in the mini tab to get that value. Hopefully that kind of runs you through it. I'm going to let you go. Again, sorry for the background noise. And hope you guys all have a great rest of your weekend and enjoy your President's Day. Thanks so much. Bye.